Welcome to Calculus. We've taken a look at 3 examples of evaluating limits by direct substitution. Let's keep going and look at a total of 4 more examples in this segment. We'll have a total of 7 examples for evaluating limits by direct substitution. Let's head over to our notes screen to see our next example. So here we've got the limit as x approaches positive 3 of the function f of x. So just to remind how we're treating this is as a function equals x minus 2 over x squared plus 3x plus 2. So at this point, I want to really just look and see what the graph looks like for this rational function. So it's a fraction setup. So we'll create our coordinate plane. And up till this moment, we've been graphing these functions manually, and we could definitely do so for this f of x equals this rational function. But I do want to demonstrate what tools we have at our disposal if we run across something that really has a lot of evaluation, a lot of parts. So let's take a look at our graphing calculator. So I will set up the table. But I'm going to head over to an online graphing calculator that's free and is just as functional as a TI-84 or a TI Inspire. So I'm sharing this screen. This calculator is desmos.com, desmos.com. And when you type that URL, you come to this gateway site, and where we're going to hit is the graphing calculator. So I am going to input that function as we wrote it. So that's x minus 2 over x squared plus 3x plus 2. So on Desmos, I'm going to type that in. And really what I'm interested in is just catching the general shape of the graph. Again, our emphasis is on evaluating the limit by direct substitution. But I'm going to look at the graph of the function first. So in the numerator, x minus 2, denominator is x squared plus 3x plus 2. So it looks like we've got a rational function with 2 vertical asymptotes here. I'm just going to check to see, remember from algebra 2, to graph a rational function, we look for the vertical asymptotes from the factors of the denominator. So one of those definitely is going to be x plus 2, which would solve to x equals negative 2. So definitely we got that vertical asymptote on the left. The other factor of that denominator is x plus 1. So if I solve that, it'd be x equals negative 1. And again, we've got that other vertical asymptote there. Looks like the x-axis is our horizontal asymptote. So it's a rational function. And again, I'm not focusing so much on graphing real precisely. I just want to know roughly what's the shape of this graph. So with those 3 asymptotes in mind, I'm going to head back to the note screen so that I can sketch a graph and then evaluate the limit by direct substitution. So what we had seen on that graph screen was that the x-axis was a horizontal asymptote, and then we had 2 vertical asymptotes, one at negative 2, one at negative 1, and then the graph itself was on either side. So there may be something going on in between negative 1 and negative 2. We didn't do a lot of investigation, and then this one kind of rose above that horizontal asymptote and then assumed its value on the right. Well, we're interested in what's going on this graph at positive 3. So just like we've done on previous examples, I really want to say what's happening to the y value as x approaches 3 from the left. and from the right, and that y value is going to be our evaluation of the limit. So in my chart here, the only number that I really want to evaluate is 3. So we're going to calculate f at 3. So from this function that we wrote in green there, I'm just going to substitute every x with the specific value of 3. So it becomes 3 minus 2 over 3 squared plus 3 times 3 plus 2. And let's evaluate that fraction. So 3 minus 2 is going to give us the difference of 1. And then for the denominator, it's going to be a large denominator. This is 9, 3 squared, plus 3 times 3 is another 9. So 9 plus 9 is 18, plus 2 is 20. 1 over 20. We can write that as a fraction, in fact, so we'll just keep it as is. And here's how we would record our answer. The limit as x approaches 3 of the function x minus 2 over x squared plus 3x plus 2 equals 1 over 20. So just like we'd seen in our first 3 examples, this fourth example can be evaluated directly just by substituting the limit value into the function. I do want you to graph and give a rough sketch of that graph so that you can see conceptually what are we looking for. We're looking for the y value of the function as x gets close to the number from the left and from the right. And it's got to be the same on each side for that limit to exist. So we've looked at a variety of functions. Let's take a look at a radical function. So here we've got the limit as x approaches 3 over 2, so the decimal 1.5, of the function square root of 2x minus 1. So I want to sketch that graph, create the coordinate plane. And really, just to emphasize this, the graph's purpose is really just so we can see roughly what's happening with the function around that value 1.5. And does it look like it's continuous on the graph? So again, I want to use, I think on this one, we could probably head to the calculator as well, just to see what is looking with that function. So we'll write it. It's f of x equals square root of 2x minus 1. Definitely, this is a function we could use a table to evaluate. But since our limit value is a decimal, 3 over 2 or 1.5, let's just get the graph's rough shape. And then we can evaluate by direct substitution. So we're going to plug that in. Let's head over to Desmos. And we'll clear out the function we had just looked at. And type in the new one. So f of x equals, and there's 2 ways to put square root. You can type in sqrt, which will convert to square root. There's also a dedicated key here on the keypad, the lower part of that main keypad. So 2 ways to input square root. So just to be sure, let's check on that function. It's 2x minus 1. 2x minus 1. So it looks like we've got the square root function. It's got its vertex here on the x-axis at half, since each of these hash marks is equal to half. And then it rises pretty quickly. Looking for some places where it crosses. Looks like it crosses at 2.5 and 2. So that gives us enough information to sketch a graph. Let's head back to our notes screen to do so. So here on our coordinate plane, we'll go with vertex there at half, and then I believe at 2.5, it was at the y value of 2. So roughly there, and that gives us a rough shape for our square root function. Now again, what we're interested in is what's happening to the y value when x gets close to 1.5. So I'm going to trace up to the graph, and really it's that y value there. So probably we could estimate that that's 1.5. Let's see if that's accurate. So we're really saying what's happening to the y value as x approaches 1.5 from the left and 1.5 from the right. So we're ready to do the direct substitution. So we're going to calculate f at 3/2. So I'm going to keep that as a fraction because it looks like it'll be real useful when we substitute. So that's the square root of 2 times 3/2 minus 1. And we'll simplify that. So our 2's will cancel. 2 divided by 2 is 1. So that becomes the square root of 3 minus 1, which is the square root of 2. So our estimate was okay. Keep in mind, square root of 2 is about 1.414. So our estimate of 1.5 was roughly good. So we'll finalize our response here though. So the limit as x approaches 3/2 of the function square root of 2x minus 1 equals the square root of 2, which is roughly 1.414. And that, again, that's our answer. The graph is there just to support the idea of what's the limit asking for. What is the y value as x approaches that number under the limit? So we want to take a look at some trigonometric functions. We've seen a lot of these algebra 2 functions, and that's a good review for us. Trigonometry is given to us in geometry and pre-calculus, so it's good to remember how to evaluate for cosine and sine and so forth. So here I've got the limit as x approaches pi/2 of cosine of negative 2x. Let's take a look at the graph of this function. So we're looking at f of x equals cosine of negative 2x. And I'm going to sketch this in the traditional trigonometric coordinate plane. So it really focuses on the positive x-axis. Excuse me. And let's subdivide that into, let's see. Let's go up to pi. So we'll go pi/2, and then we'll look also at pi/4 and 3 pi/4. So we'll go those intervals, and let's create a table of values so that we can evaluate here. So notice we're going to actually do the direct substitution for the x value or the theta value of pi/2. So we'll put those. Let's start with 0, pi/4, pi/2, 3 pi/4, and pi. And here's our function column. So for this first one, we want to evaluate what is f at 0. F at 0, sorry, I was trying to get the red color. So we are substituting in for x, so that's cosine of negative 2 times 0, which is cosine of 0. So recall from the unit circle, if I'm on the unit circle at 0 radians, That's right here on the positive x-axis. So cosine is x over the radius. So remember at 0, that x is identical to the radius. So cosine of 0 is 1 over 1, which is just 1. So we've got the initial point 0, 1. We'll keep going. So we're going to calculate f at pi over 4 is cosine of negative 2 times pi over 4. So we got to simplify that product. That's cosine of negative pi over 2. So we are going in the negative direction of this unit circle. So that goes down there. And negative pi over 2. So the x value at that lower y-axis is 0. 0 over the radius of 1 is just 0. So at pi over 4, we're at 0. We'll keep going. So f at pi over 2 is cosine negative 2 times pi over 2. And those 2's cancel there in the product. 2 divided by 2, or 2 times half. So this is cosine of negative pi. So it's going around the unit circle in the kind of the clockwise direction. It's the negative direction. And there we've got the value. Let me mark these. This is pi over 2, negative pi over 2, negative pi. The x value at negative pi is negative 1. Because we're over here on the left side, it's negative over the radius of 1. So that's a value of negative 1. So you can see that oscillation starting. So pi over 2 is at negative 1. And then our next value is 3 pi over 4 is cosine of negative 2 times 3 pi over 4. Again, we got to simplify that product in the inside for the theta value. That's cosine. Negative 2 over 4 becomes negative 1 over 2. So that's negative 3 pi over 2. So no surprises. We're back up kind of a quarter turn, negative 3 pi over 2. And that again is 0. Anytime we're at the y-axis, the cosine x value is 0. So you can see this oscillation, 1, 0, negative 1, 0. Can you predict what the next one will be? F at pi is cosine of negative 2 pi. And that's back to what we've been calling 0. Remember, the unit circle cycles around and repeats as you wind around the unit circle. So that's equivalent to cosine at 0, which is again 1. Okay, so we're ready to just sketch that graph. And the good news is we've done our direct substitution evaluation for the limit as part of this table. So we don't have a whole lot to do once we've graphed this and seen what we're looking at with the limit. So let's sketch the graph. So there's 1, there's negative 1, and there's 0. So we start up here at 1 to 0 at pi over 4, to negative 1 at pi over 2, to 0 at 3 pi over 4, and to 1 at pi. So we'll fill in that framework with our cosine curve. And remember, the cosine curve is infinite in the x direction. It just keeps like a wave. So definitely what we're looking for in terms of the limit as x approaches pi over 2 is what is the y value as x approaches pi over 2 from the left and from the right. They have to equal each other. It looks like we're in good shape here. So we can go ahead and record our final answer. The limit as x approaches pi over 2 for the function cosine of negative 2x equals, Let's check out our output here for pi over 2. We can see it here on the graph. If we trace over to the y-axis, is -1. All right, so that's our third example here. Let's round this out by looking at a sine function. And this will be our last example for direct substitution to evaluate limits. So here we've got limit as x approaches pi over 4 of negative sine of x. So we'll bring our trigonometric coordinate plane there. And again, let's just use this t-chart to evaluate. So let's go with the same increment, 0, pi over 4. And this does the double duty of actually evaluating that limit value for x. Pi over 2, 3 pi over 4, and pi. F of x here is going to be negative sine of x. And let's put our unit circle just so we've got that reference. When you're doing trigonometric graphing, you do want to have the unit circle close at hand, at least sketch it so that you can bring it out of the memory. And if it's not in the memory really strongly, it helps to recreate the unit circle to kind of spark those memories. All right, so we're going to start by calculating f at 0, which is negative sine of 0. So recall unit circle when we're at 0, the y value, remember sine is y over the radius 1. Well, at the x-axis, y value is 0. So we're starting at 0 here. So this begins at the origin, 0, 0. We'll calculate f at pi over 4 is negative sine of pi over 4. So notice our x here is positive. So what we're doing is we are traveling in the the positive direction on the unit circle. Let me draw that better. So pi over 4 is 45. Remember, we're looking at that right triangle. And that's that special 45, 45, 90 triangle. So that is the case when cosine and sine are both the same. They're both pi square root of 2 over 2. So that's negative square root 2 over 2. Hard to graph that one. That's a very irrational number. But this next one will help. So f at pi over 2 is negative sine pi over 2. So pi over 2 is at 90. So we're moving in slightly shorter pieces of that circle, shorter arc lengths. So that pi over 2 is 90. And remember, at 90, the y value is 1. So 1 over radius of 1 is 1. Now I do need to tack that negative on there. Okay, so moving along the unit circle, f at 3 pi over 4 is negative sine of 3 pi over 4, which is, again, we're here at the 45. So still it's the same value because we're above the x-axis. So the y part there of that 45, 45, 90 triangle is still square root of 2 over 2. The negative is coming to us from the function. See, the function had a negative tacked onto the front of sine. Well, let's finalize this sketch of the graph by evaluating f at pi is negative sine of pi. And pi, again, takes us all the way back down to the x-axis, which again is a y value distance off the x-axis. On the x-axis is 0. So let's record these points. At pi over 4, we're at negative pi square root of 2 over 2. pi over 2, we're at -1. 3 pi over 4 evaluates negative square root of 2 over 2. And then pi itself is back at 0. So it does show that oscillation, but it's a little longer curve. Let's partition our x-axis here. So 0, pi over 2. And between those guys, we'll put pi over 4. There's pi, and between those is 3 pi over 4. So here's our 1, our 0 on the x, and -1. So this starts at 0, and I'm going to sketch over here pi over 2 is at -1. So our sine curve here, we kind of have a bigger wave. And again, keep in mind, it keeps going both directions. What we're seeing is just one trough of the wave here. So just to check for the limit we're looking at, we're looking as x approaches pi over 4. So it looks good in terms of continuity. That left side is matching up with the right side. So we're ready to write our answer because we've actually calculated already f at pi over 4. That's our direct substitution. So our final response here is the limit as x approaches pi over 4 of the function negative sine of x equals the negative square root of 2 over 2. Let's get a decimal approximation. So that's again a good use for Desmos. Really difficult to calculate the square root of a prime number just by hand. So let's just calculate negative square root of 2 over 2. And Desmos estimates that at negative 0.707. Okay, we'll head back to our note screen to finalize that answer. So that has the approximate value of negative 0.707. And that concludes our segment here on evaluating limits by direct substitution. So we'll take a look at some other strategies when you can't directly substitute your x value into the function, but that's for the future. Thank you for joining. See you soon.